Hello everyone, welcome to the third lecture of this seventh week where we are discussing about transducer, and this is the third module of our course on measurement and instrumentation. So I hope that till now you have a basic idea of the characteristics of a transducer. Of course, many of the characteristics we have seen in our first module, which was in general for different analog instruments as well as for the transducers, but for specific transducers we have also seen certain characteristics. All right. So today we are going to discuss or we are going to start actually the different transducers which we promised to discuss. Okay, but before I actually jump into different transducers, I would say let's recall the definition of transducer. We should not forget that. Okay, so we have learned in our first lecture in this module as well as in the previous modules also that a transducer usually convert non-electrical signal into electrical signal for measurement as well as for control systems. Okay, and we have seen a broad way of classification of the transducers, but if we summarize whatever we have seen, okay, we can say that transducers can be defined or can be classified based on the transduction principles as well as based on the measurement that it is measuring. Okay, so based on the transduction principles we have a number of transducers, like we can have resistive transducers, inductive transducers, then we can have transducers which work on based on change in capacitor. So we have capacitive transducers, then piezoelectric transducers, piezoresistive transducers, thermoelectric transducers, photoelectric, or sometime also it falls under optical transducers, okay, or Hall effect transducers, magnetic transducers, and so on, right. So this is based on the transduction principles, right. Now we have transducers based on the measurements also. Okay, so based on measurement, like what is actually it is measuring, okay, we have temperature sensors. So we have a non-electrical phenomena, say heat flow or rise in temperature and so on, okay, to convert it into certain another form. Okay, so we have temperature transducers, then pressure transducers, displacement transducers, force or say strain transducers. For flow monitoring we have flow transducers, then for water level monitoring we have level transducers, light transducers, humidity transducers, speed transducers, and so on. Please note that whatever we have seen for the transducers based on transduction, those things can be extended here. For example, what I mean to say that for pressure monitoring, for example, okay, say pressure transducers, I can have, okay, resistive transducers working as a pressure transducer. I may have capacitive transducer working as a pressure transducer. I may have piezoelectric transducer or thermoelectric transducer working as a pressure transducer. What I mean to say that based on measurement, say if I have this say transducer classification, now this transducer can have multiple techniques for the transduction or multiple principles of transduction. It can be based on capacitive, it can be based on resistive, okay, and so on, right. So it's kind of jumbled kind of situation, and that's how we have to deal with. Okay, so what we will do is we will learn about some of the generic transduction techniques, and then we'll see that with certain examples that how it can be extended for measurement of certain parameters. Means that we will learn the transduction techniques based on the principles, okay, and then we will see that how these transduction techniques that we are seeing can be extended for the measurement of number of measurements. Say the same transducer can be extended for the measurement of force, how it can be extended for the measurement of say temperature, how it can be extended for the measurement of humidity, and so on. Okay, so in this series let's learn the first fundamental transducer, which is very important for our general use also, and industry also rely on it a lot. Okay, and we call it strain gauges. Okay, so let's learn about strain gauges, and this is a very important classification of or important part of the transducer section. Okay, and mostly it is based on piezoresistive kind of principle, and let's see that how a strain gauge can be extended for the measurement of stress and other parameters. Okay. So this is based on, as I have mentioned, piezoresistive principle. So if a metal conductor is stretched or say compressed, its resistance changes on account of the fact that both length and diameter of the conductor changes, and this is coming from the well known formula of resistance, which is equal to rho L by A. Okay. So if I have a metal wire, for example, having a cross section area of A, okay, and length of L, okay, and the resistivity of the material, is say rho. Okay. So this material I am talking about, this conductor is made up of. Okay. Now the resistance is given as rho L by A. This formula we are aware of, right? Now I am telling that you are applying a certain stretch or say compress. So you are applying basically a force of compression, or basically stress you are applying. You can either stretch it or you can compress it. In both the cases, basically the dimensions are changing. Okay. So if you are stretching it, means that say earlier length was L and now you have increased it. Okay. Now it is say for example L1. So initially it was L1 for example, now it is L2, means that the length has increased when you have stretched it. Okay. However, on the same time this area is also changing, the cross section, because the diameter will decrease, right, because the material is same. So when you are stretching, this area is or diameter is changing. Okay. Because of change in L and A, there will be a change in the resistance. Okay. Please note that there is also a change in the value of resistivity of the conductor when it is strained, and this property is known as the piezoresistive effect. So if it was only the effect of L and A in the case of this resistance, okay, it was phenomena occurring in all kind of materials. But when you have change in the value of resistivity also, means that this material is behaving as a piezoresistive material. Okay. So therefore the resistance strain gauges are also known as piezoresistive gauges. So whatever strain gauge we are discussing right now are a kind of piezoresistive gauge or say resistive strain gauges. Okay. The strain gauge are used for the measurement of strain and associated stress in experimental stress analysis, and you will find people across all the discipline, be it electrical, be it electronics, mechanical, civil, everyone usually use strain gauge for maybe different purposes. Okay. So the change in the value of resistance by straining the gauge may be partially explained by the normal dimension behavior of elastic material. Okay. So if a strip of elastic material is subjected to tension or say positively strained, as you can see over here, you had kind of, you are stretching it, means that you are decreasing the diameter and the length is increasing by certain value, say delta L, and this is the positive strain direction. Okay. Now its longitudinal dimension will increase while there will be a reduction in the lateral dimension. Okay. So when a gauge is subjected to a positive strain, its length usually increases while its area of cross sectional will decrease. Okay. Since the resistance of a conductor is proportional to its length that we have just seen and is inversely proportional to its area of the cross section, the resistance of the gauge increases with positive strain. Okay. Now the change in the value of resistance of strained conductor is more than what can be accounted for an increase in resistance due to dimension changes. Okay. So if you have say R1 value, okay, for initial resistance for example, so R L1 by A1, okay, and say initially the resistance was this, and say when you have applied say positive strain and R2 increases to certain value, say R2 is equal to rho, say I am calling it rho 1 rho 2, okay, L2 by A2, okay. Now in this case R2 is greater than R1, okay. Now usually you expected that, okay, there will be change in L1, of course you can quantify them that. So there is a change in L1, there is change in A1, okay, or in the, say, change in L1 is certain value, say delta L, and now it has become L2, and similarly change in A1 is, say, delta A, and now it has become A2, okay. So R2 has become rho 2 into L2 by A2, okay. However, mathematically you are not able to match this. What I want to say is, say, this value, whatever you are getting, okay, ideally, should match with the increment value to the initial value, okay, if you are only accounting for L2 and A2. However, it is not happening, for example, okay, and change is even more, okay, means that there should be, deviation in this rho 1, means that rho 1 is also changing, so that certain del rho value is getting added or subtracted from this, and that's how you are getting another resistivity. Usually we think that resistivity is a property of material, okay. However, here with the apply of application of the strain, this value is also changing, okay, and this extra increment in resistance is actually accounted by the piezoresistive behavior, okay. So the extra change in the value of resistance is attributed to a change in the value of resistivity of a conductor when it is strained, okay, and this property, as described earlier, is known as the piezoresistive effect, okay. So this property, as described earlier, is known as piezoresistive effect, okay. Now let us consider strain gauge made up of circular wire, okay, something like this. The wire has the dimension, initial dimension, say L is the length, A is your area, okay, and this is, say, diameter is, say, D, as we have seen earlier also, okay, and the material of the wire has a resistivity of rho. Therefore, the resistance of unstrained gauge is equal to rho L by A. So initial resistance when there is no strain applied, okay, the resistance is equal to rho L by A. Now let a tensile stress S be applied to the wire. This produces a positive strain causing the length to increase and area to decrease, as shown earlier also and shown over here also. So you applied a stress, and because of which this diameter has changed to D minus del D, while the length has increased from L value to L plus del L value, right. Now when the wire is strained, there are changes in the dimensions, okay. Let del L be change in the length, del A be the change in the area, del D be the change in the diameter, and del R is the change in the resistance, okay. In order to find how this del R change in the resistance depends upon the material's physical quantities, the expression for R is differentiated with respect to stress S, okay. And what was the expression for R? The expression for R was rho L by A, alright. So if you differentiate it with respect to S, you have to, since all these values are changing with respect to stress that we have just seen, okay, we have to, say, differentiate each quantity keeping others constant. So if I differentiate this R with respect to S, say differentiate for example first L keeping rho and A constant, you will get this value, say I am calling this 1, okay. So when you differentiate this L, you will get this rho by A into del L by del S, okay. This is, say, first. Second term is when you differentiate it with respect to S, okay. Differentiate rho while keeping L and A constant, you will get L by A del rho by del S, say this is 2, okay. Now the last is differentiating the area, okay, keeping rho and L constant, means that you will get rho L by A square del A by del S and a negative sign, right. This is your third term. So if I have to write dr by ds or del R by del S will equal to all these three terms added together, okay. So this term is when you are differentiating value L, right. This term is when you differentiate area A, and this is differentiating the resistivity. And these terms we have calculated by keeping other two terms constant. Say for example, the first term differentiating the value of L by keeping rho and A constant, right. So, this is equation for dr by ds. So, I am calling this equation 1 for example. Okay, fine. So, this is our equation 1 that we have just seen. Now, if I divide this equation throughout by resistance R, okay, which was the rho L by A, what we will get is this dr by ds into 1 by r, since we are dividing this. Okay, so in your LHS you have 1 by r dr by ds. Okay, this side when you divide it by rho L by A, okay, what you get is basically rho by A into A by rho L. Okay, so rho get cancelled and A get cancelled, and you have 1 by L del L by del S. Similarly, for other term you have minus 1 by A del A by del S plus 1 by rho del rho by del S. Okay, I am calling this equation 2. Okay, so 1 by R del R by del S is equal to 1 by L del L by del S minus 1 by A del A by del S plus 1 by rho del rho by del S. Okay, this is my equation 2nd. Now, it is evident from this particular equation 2 that per unit change in resistance is due to per unit change, because we have divided it by R, means that per unit change in the resistance is equal to per unit change in the length. So, this term del L by L, okay, per unit change in the area del A by A, and per unit change in the resistivity. Okay, so per unit change in the resistance is due to per unit change in the length, per unit change in the area, and per unit change in the resistivity, and this is a very important concept to learn from these strain gauges. Now, let us recall our wire which were having say diameter D. Okay, so if I have to write area A in terms of D, so we know that area is equal to pi r square, or say pi d by 2 square, okay, because we are having diameter, not the radius. Okay, so you have pi d square by 4. So, you have area equal to pi d square by 4. Okay, now let us calculate del A by del S. Okay, so if I calculate del A by del S, it is equal to 2 into pi by 4 into d, then del d by del S, or 1 by A. Okay, if I again normalize it, 1 by A del A by del S is equal to 2 pi by 4 d by pi by 4 d square into del d by ds, or if you simplify it, you get 2 by d del d by del S. So, 1 by A del A by del S is equal to 2 by d del d by del S, and I am calling this equation say 3. Alright. Now, let us recall our equation 2, where we had got 1 by r dr by or del r by del S is equal to 1 by L del L by del S minus 1 by A del A by del S plus 1 by rho del rho by del S. And now, from equation 3, if I substitute this second term in this is the second term, okay, which we have got in the form of the diameter, which is 2 by d del d by del S. Okay. Now, if I replace this the second term with the whatever value we have got in equation 3, we get 1 by r del r by del S is equal to 1 by L del L by del S minus 2 by d del d by del S plus 1 by rho del rho by del S, and I am calling this equation say 4. Okay. Now, this equation is very important, and it is the basis for several analysis for the strain gauges. Okay. Let us see some of the factors. Okay. Now let's for example define a Poisson's ratio. Okay, so Poisson's ratio is equal to lateral strain by longitudinal strain, and this is equal to minus del D by D, which is the lateral strain, and longitudinal strain, which is del L by L. Okay, so del D by D can be equated with minus of Poisson's ratio into del L by L. Okay, now recalling the normalized equation from equation 4, okay, in this case what we get is just replace this del D by D, okay, with this particular value, okay, minus Poisson's ratio into del L by L. Okay, so if you replace this value in of the second term in equation 4, what we get is 1 by R del R by del S is equal to 1 by L del L by del S plus Poisson's ratio into 2 by L del L by del S plus 1 by rho by del S. Okay, so for small variation, this relationship, say I am calling this equation 5. So for small variation, this relationship can be written as del R by R, okay, equal to del L by L, okay, plus 2 into this Poisson's ratio into del L by L plus del rho by rho. Okay, this equation is very important for our strain gauges. Okay, so change in the resistance value is equal to del L by L plus 2 into Poisson's ratio del L by L plus del rho by rho. Okay, now you can also define a gauge factor for a strain gauge. This is kind of a factor based on which you can compare different strain gauges. So the gauge factor is defined as the ratio of per unit change in the resistance to per unit change in the length. So gauge factor, this gauge factor GF is equal to del R by R into del L by L, okay, or del R by R is equal to GF into del L by L. Okay, now this was the strain, okay, and say if I denote a strain by say this epsilon, okay, so the change in resistance by R del R by R is equal to the gauge factor into the strain. Okay, so per unit change in the resistance is equal to gauge factor into the strain value, and say I call it equation 6. Okay, now the gauge factor can be written as from this equation you can simply write gauge factor as 1 plus 2 into this Poisson's ratio plus del rho by the strain. Okay, so this is equal to resistance change due to change in length, the first factor, plus resistance change due to change in the area, this factor, plus resistance change due to the piezo resistive effect. All right. So this is how you can write the gauge factor. Okay. Now since you have also defined it as del R by del L by L, so this is equal to 1 plus 2 into Poisson's ratio plus del rho by del L by L. The strain is usually expressed in terms of micro strain. So 1 micro strain is basically 1 micrometer per meter. Okay. So if the change in the value of resistivity of a material when strain is neglected means that the third factor you are actually neglecting. Okay, when you are not considering this, the gauge factor can be simply denoted as 1 plus 2 into this new value, which is the Poisson's ratio. This equation is valid when the piezo resistive effect or the change in the resistivity due to strain is almost negligible. Okay, in those cases you can consider the gauge factor as this, okay, 1 plus 2 into Poisson's ratio. So the Poisson's ratio for all metal is usually between 0 to 0.5. Okay, this gives this gauge factor. So this ratio is a 0 to 0.5, means maximum it can have a value of 0.5 for example. Okay, so the total value will be 1 plus 2 into 0.5. So usually maximum will be around 2. Okay, so this gives the gauge factor of approximately 2. Okay, The common value of Poisson's ratio for wires that we deal with is around 0.3 to 0.4, and this gives a value of around 1.64 or 1.7 for wire wound strain gauges. Okay, and these values not very important to remember, but then you should know that what is the range of Poisson's ratio for metals and semiconductors. We will discuss about semiconductors also. Okay, but if you remember the ranges, I think that will be good. Okay. And if I have to classify these strain gauges, they are broadly used for two major type of application. They are like experimental stress analysis of machines and structures that we discussed some time back, and then construction of various transducers. Okay, so you can use the strain gauges to construct a transducer for the measurement of force, for the measurement of torque, for the measurement of pressure, flow, acceleration, etc. Okay, all can be based on strain gauges, but maybe how the strain is changing, how the measurement is changing the stress might be different. Okay, so there are different types of strain gauges, and some of the types are written over here. Okay, you have unbonded metal strain gauges, you have bonded metal wire strain gauges. Okay, we have this wires sometimes can also be used in the form of foils. So you have bonded metal foil strain gauges. Okay, then we have thin film based strain gauges. So metallic film can be deposited by number of means, by mostly by sputtering. Okay, we have sputter deposited thin film strain gauges separately. Okay, so then we have bonded semiconductor strain gauges, because as I have mentioned earlier that the Poisson's ratio and other things of the semiconductor materials are totally different than what we have just seen. So you have a bonded semiconductor strain gauges, you have diffused metal strain gauges, and so on. So you can have more number of varieties of strain gauges, but usually they fall somewhere in this particular list. Okay. So we will keep our discussion on strain gauges alive in our next lecture, where we will mostly see these strain gauges based on their construction and their way of operation. All right. So if you have that knowledge, you can extend that for constructing of different transducers for the measurement of a number of physical measurements that I have just talked about, like force, torque, pressure, and so on. Thank you.